Hello everyone. First of all, I want to thank all the organizers of this conference in material physics of University of الطارق الشاذلي بن جديد. Before starting my presentation, let me introduce myself. I am Mekki Houria, PhD student from University of Msila, Mohammed Badief. Our topic today is about half-Hessler alloys, which attracted the last 2 decades a lot of attention because of their application in spintronic and magnetoelectronics. The title of my presentation is The Electronic Structure and Magnetism in Half-Hessler Alloys, potassium, chromium, and atom Z, which represent the sulfur, selenium, and tellurium atoms. First of all, we have investigated our compound using density functional theory, DFT, based on full potential linearized augmented plane wave, implemented in code V2K. We have calculated the electronic and magnetic properties using two approximations, generalized gradient approximation GGA and modified Beck and Johnson MBG GGA. Going to the results. Our crystal structures crystallize in cubic phase center, each atom in color, potassium in green, chromium in red, and atom Z in blue. On the other hand, we have the stability of the lowest energy of our compounds, and 3 atomic arrangement type 1, type 2, type 3. As we can see here that both compounds, potassium chromium sulfur and potassium chlorine selenium, are more stable on type 1 structure, while the other structure, potassium chromium tellurium, type 3, is the most stable. Going to the electronic and magnetic properties. We have calculated the equilibrium lattice constant, bulk modules, and its derivative using GGA approximation. According to this table, our compounds or our result is in good agreement with other results. In table 2, we have calculated the total and partial magnetic moment, energy band gap, and spin polarization at the equilibrium lattice constant using GGA and MBG GGA approximation. As we can see here that our compounds have a large magnetic moment which equal to 5 per unit formula. Also a large band gap which is more than 2 electron volt. And their polarization is about 100%, which indicate those compounds have a half metallic behavior. For band structures, we start by the first compound, potassium chromium sulfur, in both approximation GGA and MBG GGA. So on the spin up direction, we show that the compounds exhibit an overlap between the valence and conduction bands, as we can see here. On the other hand, in the spin down direction, we find that both bands are separated from each other by a direct band gap gamma gamma of the value 3.14 electron volt. This is for the first compound. So this compound, in the case spin up, is metallic and spin down is a semiconductor. On the other hand, we have the density of state. Using GGA approximation, we can see that the orbital D of the atom chrom is the main contribution here. It have the main contribution, which is large comparing to other orbitals of other atoms. Same interpretation for the second compound, potassium chromium selenium, in both approximation GGA and MBG GGA. For the case spin up, our compound is a metallic, and the other spin down, the compound is a semiconductor with indirect band gap gamma X with the value 2.81 electron volt. the same thing as the first compound in density of state, that the orbital d have the main contribution when comparing to other orbitals. Going to the final compound, which is potassium chromium tellurium. Same interpretation, that this compound in the case up, spin up, is metallic, and the spin down is a semiconductor. Also in the density of state, this compound have a large contribution to the orbital d. So we find that the studied half-Hassler alloy have a band gap in the spin direction, confirming the existence of the half metallic behavior. In conclusion, our study performed to determine the most stable magnetic configuration into magnetic state. We have also calculated the equilibrium lattice constant, the bulk modules. Then the result of electronic structure shows that the compounds exhibit a half metallic character with 100 spin polarization at the Fermi level, with the largest magnetic moment, which is 5 per formula unit, and follows the modified SP rule, and large band gap more than 2 electron volts at their equilibrium lattice constants in their most stable phases. Thank you so much.